So let me start by saying, I love you. That's that's from a Lionel Richie song. Okay, but that's not what I meant to start by saying. Um, uh, the first thing is there's no class. My class on Wednesday is canceled. So Thermo is canceled Wednesday. All classes are canceled Thursday through the weekend. And I don't know about the status of the building. You should, if you're going to drive in, you should find out about that. My guess is, well, for sure on Thursday, I assume the building is closed, and I think it'll probably be closed Friday too. And then the withdraw deadline. I'm not saying this for anybody in here right now. Everybody in here is in good shape, but to get this on video, the withdraw deadline is this Wednesday. So after this Wednesday, that's not an option anymore. So, think about it. And if you're considering withdrawing from the class, it definitely is a good idea to make an appointment with an advisor first, because it can have implications for financial aid and stuff. Some financial aid it matters for, some it doesn't. So just, talk to somebody who knows about that stuff. Just make an appointment with an advisor. And because the withdraw deadline is coming up, I finally went and graded all the stuff that was emailed in late. So I think everything should be updated. So check your grades and just make sure there's no glaring mistakes, like you turned in a weekly assignment and I have a 0 for it and that kind of stuff, okay? But your grades should be updated up through, I guess, I haven't done the most recent weekly assignment yet, but everything else is done. And let me know if you have any questions about it or, whatever. So you should be able to see your overall percentage in the class right now. And so that should give you a very close idea of where your grade stands right now. We basically have a month left in the class, a shade under a month left. And these grades are going to be basically just 90, 80, 70, 60% cutoffs. So, whatever your percentage says, that'll tell you where your grade's sitting right now. And just contact me if you want to talk about it or whatever. Any questions about that? All right. The next thing I want to do, I don't think I gave you any daily assignment, right? Okay. So I just want to do an example that's a lot like the daily problems that you're going to be assigned. So this is an example of using values with the Rankine cycle to calculate stuff. The Rankine cycle that we've been dealing with so far has only been the ideal cycle. So this is an ideal Rankine cycle. Where water is the working fluid. And we know that saturated vapor enters the turbine with a pressure of 8 megapascals, 8.0 MPa. And saturated liquid exits the condenser at 0.08 megapascals. And we're told that the net power of this plant, the net power output is 100 megawatts. And we want to calculate the efficiency and compare it to the ideal efficiency. Oh, that doesn't make any sense. This is ideal, right? Yeah, very good. So we just want to calculate that efficiency, which is the ideal efficiency. We want to calculate the back work ratio. We want to calculate the mass flow rate. We want to calculate the heat transfer into the working fluid at the boiler. The heat transfer out of the working fluid at the condenser. And then last, and I'll go into some detail about how to do this calculation because I haven't done this yet, but you'll see this in a problem or two. If the cooling water in the condenser has an inlet temperature of 15 degrees Celsius and an exit temperature of 35 degrees Celsius. So this is the water that's sent through the walls of the condenser to carry away the heat from the working fluid. The question is, what's the mass flow rate of the cooling water? Okay, the first thing I want you to notice about questions like this is you look, we're talking about this thing with 4 different stages where we have all these enthalpies in our calculations and stuff. You look at the way the questions are worded and you're like, there's no way that's enough information to calculate all this stuff. But remember that in the Rankine cycle, for every process, some property at the start of the process is the same as the property at the end because we have the 2 isentropic processes and the 2 isobaric processes. So if you can calculate one pressure, you can use that pressure in a different state. And if you can calculate one entropy, you can use that entropy in a different state. Okay, so so it always is going to look like you don't have enough information. But what we're going to do is just basically we're going to write down what we know, and we're just going to start working our way around saying, okay, well, I know this is equal to this is equal to this. It's like one of those logic things in a standardized test or whatever, I'm going to start by drawing the vapor dome in the temperature entropy diagram. Here's our state 1. Here's our state 2. State 3. State 4. And based on this, notice that for states 1 and 3, all we need to know is a single property in order to define every other property, because those are on saturation. At state 2, we also only need one property, but we would also have to know the quality, because this is a mixture. Are you with me on that? And then for state 4, well, from the process from state 3 to state 4, we can assume that this is incompressible, because that's a liquid. You know, it goes from being a saturated liquid to a compressed liquid. Okay, so those are all tools that we have available. All right, so I'm going to write out like state 1, state 2, state 3, and state 4. One to 2, what's that process? Ice. We can all agree it starts with ice, something.
Isentropic.
Yes. That's the turbine, yep. The two that are constant pressure are the ones where they're just heat exchangers. Okay, so just think of it as like a big room where you're putting this stuff in and you just have heated or cooled walls, you know. So that's why it's constant pressure. So isentropic is the turbine and the pump. This is the turbine. 2 to 3, what's that?
That's the isobaric
Yep.
condenser.
Yep, exactly. Isobaric condenser. And then 3 to 4.
Pump.
Yep, that's right. Isentropic pump.
Boil it again.
Yep, and then 4, this one goes back to the other side, and this is the isobaric boiler. Okay, so we know that state 1 and state 2 have the same entropy.
Doesn't the pressure change though when you lean forward a little bit?
When you
Like coming back to your curve?
it changes going from 4 to 1, but it just doesn't change from 3 to 4.
Yeah.
Oh, 4 to, I'm sorry, 4 to 1, no, it doesn't change. Like, it's the same pressure at the, think of it as just one big room. And so the pressure is just, you know, the pump is just dumping stuff into this room, you know? And so the pressure of everything is the same inside this room.
Is it because it's a liquid? Or
Not necessarily, because the condenser, the condenser has vapor in it. It's just because it's all in contact with each other, so the pressure is just always equilibrating in both of those two cases. Okay. All right, so state 1, we know that it's a saturated vapor. We're given that P1 is 8 megapascals. Okay, it tells us that explicitly. And so since we know the pressure and it's a saturated vapor, we can use a table. Okay, so that tells us that, you know, S1 is known. We can look that up. I guess I'll just look it up right. Say we look it up right now. So this is 5.7432 times 10 to the third. That's in SI units. And the other thing that, like, in order to calculate the efficiency, what we really want are those enthalpies. If we have those 4 enthalpies, we can calculate the efficiency. Okay, so H1 is 2758 times 10 to the third, and that's also in SI units. So now look at the 2 states adjacent to this and think about what we know. It's isobaric from state 4 to state 1. So we know that the pressure at 4 is 8 megapascals. And it's isentropic from state 1 to state 2. So we know that the entropy at state 2 is 5.7432 times 10 to the third. So we haven't thought too much about anything. We saw that we could look up anything we wanted at state 1, and then we put in the stuff that we know is the same as state 1. So now let's look at the other information we're given. We're told that saturated liquid comes out of the condenser at 0.08 megapascals. Which state is that?
3.
Yeah, so state 3, we know the pressure. So state 3, and I'm going to write this is a saturated liquid. P3 is 0.08 megapascals. So that means we can look everything up. And so here we'll get the entropy and the pressure again. So H3 is 173.88 times 10 to the third in SI units. And where did I put the entropy? I guess I didn't even look that up, so I guess we can calculate. So I guess we're just going to use the incompressible assumption instead. But I mean, I could have just as easily just looked that up. I don't have the table sitting in front of me. So what do we know based on this? Well, we could know the entropy in state 4, but I didn't look it up here. So instead, the only thing that we know is that the pressure at state 2, because this is an isobaric process, is 0.08 megapascals. Um, okay, so let's so state 2, we can, like our goal is to get all of these H's. We can calculate the quality at state 2. Because we know that this is in saturation, it's inside the vapor dome. And so we can look up S for the liquid is 0.5926 times 10 to the third. And the specific entropy for the gas is 8.2287 times 10 to the third. And we know the actual entropy. So now we can say 5.7432 times 10 to the third is equal to x times 8.2287 times 10 to the third plus 1 minus x times 0.5926 times 10 to the third. And that lets us calculate that quality. So the quality here is 0.6745. That's the only state where the quality matters. But now, because state 2, if you just keep referring back to this temperature entropy diagram, and see what state you're in. The only one where quality is a thing is at state 2. But why does it help now to have the quality at state 2?
So we can figure out what the enthalpy is.
Right, exactly. So we can look up now the liquid enthalpy is 173.88 times 10 to the third. The gas enthalpy is 2577 times 10 to the third. And now we can say that the enthalpy at state 2 is 0.6745 times 2577 times 10 to the third plus 1 minus 0.6745, which is 0.3255, right? Times 173.88 times 10 to the third. And you get a specific enthalpy at state 2 of 1795 times 10 to the third. Okay, so our goal is to get all these enthalpies. I'm just going to start putting boxes around the ones we know. So we know enthalpy at states 1, 2, and 3. And now we're going to use the incompressible assumption. Remember, I could have just looked this value up, but if I give you the values in a question, You know, if I don't tell you it's water or whatever, I just give you values. You should be comfortable doing it either one of those two ways. Okay, so we're going to go for incompressible from state 3 to state 4. And the incompressible thing that we learned last time was so 3 to 4 is isentropic. I have to think about this for a second. We started with the TDS equations, and it was dH minus V dP. And it's isentropic, so this is 0. So we had that the change in H was equal to, since that V is constant, this is equal to V times the change in P. And so we have H4 minus H3 is equal to the specific volume of water, which is always right around 0.001 in SI units, times the change in pressure, pressure 4 minus pressure 3. The pressure at 4 is 8 megapascals, pressure at 3 is 0.08 megapascals. We are trying to calculate H4. So H4 is equal to 0.001 times 8 times 10 to the 6 minus 0.08 times 10 to the 6 plus H3, 173.88 times 10 to the third. And so you get H4 is equal to 181,872 in SI units. And in these problems, once you have all 4 of those enthalpies, answering you can really just go into these problems, calculate the enthalpies, and not even read the problems until you get these, Once you have these 4, you can just sort of bounce around answering the questions, usually. Okay, so now that we have those 4, our part A is what's the efficiency? That's 1 minus the quantity H2 minus H1 over H1 minus H4. And so all you're doing is plugging in these values. 1795 times 10 to the third minus 174 times 10 to the third divided by 2758 times 10 to the third minus 182 times 10 to the third. And you get an efficiency of 0.371. So 37% efficiency. And that's pretty low for an ideal efficiency. It looks pretty low, but we're going to get values around there under 50% most of the time. If this was your power plant that you were trying to make money off of, how could you boost that efficiency? I mentioned this at the end of class last time. There's sort of 4 ways you could do it.
raise the boiler, would it be temperature or pressure?
Yes, right. And there's two other ways.
Lower the condenser temperature or pressure?
Yep, exactly. So you want the boiler to be a high pressure, high temperature, and you want the condenser to be a low temperature, low pressure. And
Would you say you're trying to maximize the like delta H kind of?
let's see, what are you trying to? You are, well, I think the easiest way to think of it is in terms of temperatures. You're trying to make the ratio of the cold temperature to the hot temperature as small as possible, because the ideal efficiency is 1 minus TC over TH. So you're trying to make that second thing that you're subtracting as small as possible. So you can do that by making the boiler temperature really high, or you can get a perfect ideal efficiency by going to absolute zero in the condenser, but that's expensive.
But that's just like allowing you to exchange more entropy.
Yeah, what is that doing? That is,
Or produce more entropy.
so for these ideal efficiencies, remember we're not producing, so everything we're doing is not producing any entropy. It's just moving energy around, you know. Well, I guess that's what everything is doing. But yeah, I mean, whatever entropy you gain somewhere is being lost somewhere else. We haven't talked about, later we'll talk about actual cases where you are producing entropy.
I see what you're saying. After the ideal stuff, we're just moving it around.
Yeah, right. Okay, so the second part. We are trying now to calculate the back work ratio. So the back work ratio is something that you're trying to minimize. That is the pump energy, because that's energy you have to supply, divided by the turbine energy, because that's energy you're getting. So you want that ratio as small as possible. So this is W pump dot over W turbine dot. And you can always think of this as W pump dot over the mass flow rate divided by W turbine dot over the mass flow rate. The reason we want to do that is because we have expressions for these works. For the W dot over M dot for both of these two things. And so this is on your sheet, your notes from last time. We went through all of these. So WP dot over M dot is H4 minus H3. WT dot over M dot is H1 minus H2. And so you get 182. You can leave off the times 10 to the thirds in any ratios, because the 10 to the thirds cancel out. So 182 minus 174 divided by 2758 minus 1795. And you get 0.00831. So less than 1% of your energy that you're producing in the turbine has to be used to power the pump. And that's what you want it to be, low.
And the pump operates variably?
Instead of steady state, you mean?
Like, is that an average, or is it always using that much?
We're assuming everything's steady state. We did that to come up with the expressions for like W dot over M dot and Q dots over M dots. We always assume steady state, so it's not changing at all.
Okay.
Yeah. All right, so now we want to calculate the mass flow rate. So how are we going to do this? Well, we know that we're told that the net power is 100 megawatts. So the net power is 100, I'll do it in SI units, so 100 times 10 to the 6th. And this is the work that you get out of the turbine minus the work that you have to do at the pump. Well, we know that W dot at the turbine over M dot is equal to H1 minus H2. And that is 2758 times 10 to the third minus 1795 times 10 to the third. So 963 times 10 to the third in SI units.
Did you not just use the equation from the WP over?
I did just use that, yeah.
Oh, yeah.
Yeah, I just hadn't calculated the denominator before, you know. And then same thing with the pump, though. Yeah, we're just using the numerator now from part B. So this is H4 minus H3. And this is over M dot. So 181,872 minus 173,880. And so this is 7.99 times 10 to the third in SI units. And so WT dot over M dot minus WP dot over M dot is 963 times 10 to the third minus 7.99 times 10 to the third. So you get 955.01 times 10 to the third. And so multiply both sides by M dot and you get WT dot minus WP dot, which is equal to 100 times 10 to the 6th. That's the wattage value that we're given, is equal to 955.01 times 10 to the third times M dot. And so there's only one mass flow rate that can have all the values that we got so far, and that is 104.7 kilograms per second. Any questions about that? And now we're trying to find so this was C. Now we're trying to find the heat transfer rate at the boiler and the heat transfer rate at the from the equation that I gave you yesterday in your notes. Q dot at the boiler divided by M dot is equal to H1 minus H4. We know all these enthalpies, so subtract those and you get 2.576 times 10 to the 6. And so now Q dot at the boiler is just M dot times Q dot at the boiler divided by M dot. So that's 104.7 times 2.576 times 10 to the 6. So we get heat transfer of 2, computer, 2.70 times 10 to the 8th. This is in watts. And do the same exact thing for the condenser. QC dot over M dot is H2 minus H3, which is 1795 times 10 to the 3rd minus 173.88 times 10 to the 3rd. And then QC dot is just whatever that is times M dot. So you get 1.70 times 10 to the 8th watts. Okay, so all of these, as soon as we had the 4 enthalpies, we could just go around and do all these. The one calculation that's different is F. And this is the one where we're trying to calculate the mass flow rate of the cooling water. And so here's how to think about what's happening at the condenser. We're going to think about the control volume as the entire condenser with 2 inlets. Those inlets are the working fluid coming into the condenser and the cooling water coming into the condenser. And 2 exits, the same 2 things. So those are the working fluid and the cooling water. And we're going to assume that it's steady state. We're going to assume that there's no heat transfer. That seems funny when you first think about it. So we're going to assume there's no heat transfer for the control volume. But remember, all we're doing is assuming that the only place heat can go is from one of these fluids to the other one. Okay, and that's what the cooling water is for. So now that we're considering the control volume to also include the cooling water, we're saying that there's no heat transfer outside of our system. Okay. And no W dot. And as usual, no change in, no kinetic energy effects or potential energy effects. Okay, so we'll write out the full first law for control volumes. dE dt is equal to Q dot minus W dot plus the mass flow rate of you can think of it as the working fluid times H of the working fluid. I'll just go dot, 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 because this stuff's all going to cancel. I'm sorry, let's make this the inlet working fluid. And this also has to be inlet working fluid. Plus Mi cooling water times Hi cooling water plus dot, dot, dot. And then the exit, so minus M dot E for the working fluid times He for the working fluid plus dot, dot, dot minus Me for the cooling water times He for the cooling water plus dot, dot, dot. And all this stuff cancels. This cancels, this. Everything cancels in here except the enthalpies. We're going to assume that the inlets and exits are the same. So we just have one mass flow rate for the working fluid and one mass flow rate for the cooling water. And all this just comes out to say 0 is equal to the mass flow rate for the working fluid times the quantity H2 minus H3 plus the mass flow rate of the cooling water times the quantity H inlet minus H exit. And this is for the cooling water. And this is incompressible with constant pressure.
That's just because it's water. We're making that assumption.
Yeah, just because it's a liquid, any liquid. And so with these assumptions, we can say so all of this stuff we can calculate from before. So 0 is equal to 104.7 times H2 minus H3 So H2 minus H3 is 1.62 times 10 to the 6 plus the mass flow rate of the cooling water times this difference in enthalpies. And now we're going to use incompressibility of this and constant pressure to calculate this change in enthalpies. So since it's incompressible with constant pressure, the change in specific enthalpy is just equal to C times the change in temperatures. That's because neither the pressure or the specific volume change. And so C, this is 4186 for water. So we have 4186. We were given a final temperature. Well, we were given a starting temperature of 15 degrees Celsius, an exit temperature of the cooling water of 35. And so 0 is equal to 1.70 times 10 to the 8 plus the mass flow rate of the cooling water times uh, 83,720. And so the mass flow rate of, this should be negative. And so the mass flow rate of the cooling water is 2,030.58 kilograms per second. 20 times as much mass flow rate for that water that's cooling the working fluid than the working fluid itself.
So could you think of that as like the exhaust?
Yeah, I mean, think of that as like that's like the coolant going in your radiator to remove heat from the engine, Like the only job of that cooling water is to take heat away from the working fluid as it goes through that condenser.
And would that be slower if the source it's removing heat from wasn't so hot?
I mean, I guess it's always just it's a design parameter for you to choose as the engineer, But I guess the more mass flow rate you have, it's true that you wouldn't, like, you could make it function with less mass flow rate if you weren't trying to remove so much heat, The more mass flow rate you have, the more heat you're removing and taking from the working fluid into the cooling water.
And so they calculate that based on how fast like conduction will work in the system?
Yeah, that's right. Whew, any questions? Okay, that's all. I'll give you a couple questions like that, not too much. It's Thanksgiving. Do you guys know the song Alice's Restaurant, the greatest Thanksgiving song? Yeah, I know you know it. That's right up your alley. Well, did you hear that Alice of Alice's Restaurant just died last week?
No.
The week before Thanksgiving. I mean, she lived a full life.
Yeah, I was gonna
Well,
say,
all of you should go to your local library and look up Alice's Restaurant. Actually, the movie Alice's Restaurant that's based on the Arlo Guthrie song and I don't know if it's directed by Arlo Guthrie, but definitely like he made this movie and he stars in it. Got really good reviews actually. Like Siskel and Ebert, I think, called it the best. Or maybe it was just maybe they weren't together yet at that time. But one of them said that it was something like the third best or sixth best movie of 1969, Alice's Restaurant. It's this super crazy hippie like drug movie.
Is it about dodging the draft?
It's basically it goes through the whole song, and it's funny at times, but it's also like serious, you know. But this song, it's a song. It's basically him playing guitar while he recites this story, and the story goes he went to go visit his friend Alice, and when he got there for Thanksgiving, he went for Thanksgiving. When he got there, he thought it would be like a nice gesture since she was having him for Thanksgiving to take all her garbage and throw it away at the dump. But he goes to the dump and it's closed for Thanksgiving. And so he and his friend are like, oh, shoot, we didn't plan on that. So they're driving back, like their microbus is full of garbage. So like, now what are we, that sucks. But then as they're driving back, they go by a cliff and they see a huge pile of garbage at the bottom of the hill. So they're like, oh, well, that's, garbage should be together. So they throw their garbage. They're like, it must be fine to throw garbage here. So they throw their garbage down there, but it's littering. And so the cops go and look at it and they find an envelope with his name on it. So they arrest him for littering. And then he finally is let off with a small fine, and it seems like it's over. But then it's the draft for the Vietnam War, and he goes to the draft office and finds out he gets out of the draft because he has this criminal record for littering. And yeah, I think that's about the end of the song.
Yeah. Well put. I was waiting to like
Correct me.
Yeah, no, or like add something that
Yeah.
you missed, but you pretty much nailed it.
Yeah,
And it's really funny.
it's really funny.
Because like all the people he's there in the office with are like true criminals.
Yeah, right.
It was like mother rapists and
Yeah, and he's like, at one point, he's like, and they said, "What are you in for?" And I said, "Littering." And they all moved away from me on the bench until I said, "And creating a nuisance?" And then they all came back, shook my hand, and we had a wonderful time filling out forms and playing with the pencils on the bench.